Our big idea so far is that if I want to find distance traveled, I can find the area under the velocity curve as long as velocity is positive. And now that I know the area under velocity curve can give me distance traveled, now I see why the founders of calculus, the inventors of calculus, wanted so much to figure out how to find areas under curves. So before we really get into how to do that exactly, let's talk about how they started to approximate the answer. So there's a really nice parallel here if you're ready to see it. Remember, we wanted first semester to find the slope of a curve. We didn't have a way to do it because every time we tried to do it, we ended up with 0 divided by 0. So we thought about picking our 2 points on our line closer and closer together. So check this out. Here we want to figure out how to find the area under a curve. I don't know how to do it yet because calculus hasn't been invented yet. But imagine this. Imagine I'm going to take, let's say I want to find the distance traveled from time 0 to 4. Here's my velocity curve, 1/8 t squared plus 1. Imagine breaking this up into rectangles. And the rectangle's not going to fit perfectly because I don't have linear tops here. But, you know, if I just wanted to start by make an approximation, I might pretend for a second that I could draw in rectangles. I'm going to find the areas of those rectangles and add them up. That will give me an approximation of the area under this curve between 0 and 4. So that's exactly what we're going to do. Why rectangles? Number one, because finding the area of a rectangle is very easy. We're just going to multiply base times width. There's no number 2. So here we have to make a decision about how to choose how tall our rectangle is. You saw here I drew in my rectangle so it touched at its upper left corner. I could have just as easily chosen to make my rectangle touch at its upper right corner. But once I make that decision, I'm just going to get an approximation anyway. So here I'm going to estimate the area under this curve between times 0 and 4 using rectangles that touch at their left corners, just to see what that looks like. All right, so to do that, let's see, get this out of the way. I need to be able to figure out how tall my curve is going to be, so I filled in my time and velocity chart here. Here's my velocity function. At time 0, velocity is 1. At time 1, velocity is 1 1/8. So I just have that table there so we can refer to it. And now I can draw in my rectangle, so check this out. Let's see. And where should I go? You know important velocity fact number 1. I'm going to put me up here. So just for convenience, to kind of make it easier to see the first time, I'm going to break my time 0 to 4 up into 4 separate chunks. The chunk that goes from 0 to 1, from 1 to 2, from 2 to 3, and 3 to 4, and I'm going to cover each of those chunks with a rectangle. And I've just made this decision, just to kind of get used to it. I'm going to have my rectangles touch at their top left corner. So if I'm going to make a rectangle that covers from 0 to 1, how tall should I make it? I'm going to make it touch the curve at the left-hand side of that interval. So the interval that covers from 0 to 1, its leftmost value is 0. So I'm going to figure out what the output value is when time is 0. And that's how tall I'm going to make the rectangle. So I draw a horizontal line across here. So can I figure out the area of that rectangle I just drew? Okay, well, its width is 1 and its height is that velocity value that I just figured out. In this case, it's 1. So this is going to be 1 times 1 to make 1. My second rectangle, I want it to cover from time 1 to time 2. If my rectangles are going to touch at the left-hand corner, then I have to think of the left-hand side of the intervals 1 to 2 is 1. So I'm going to make my rectangle as tall as, essentially, v of 1. So what's the velocity when time is 1? I have that in my table here. It's 1 1/8. So can I figure out the area of this rectangle? has a width of 1 and a height of 1 1/8, so 1 1/8 as my area of that rectangle. And I'm going to keep going. My third rectangle, I'm going to have touch at 2 comma v of 2, and v of 2 happens to be 1 1/2 and then 2 1/8. Turn my marker back on. This rectangle, area 1 1/2. That's all these rectangles have a width of 1, so that's why I'm multiplying by 1. And it ends up that the area looks like I'm just using the height value. That's because I'm multiplying by the width of 1. And this was, what did I say, 2 1/8? Okay, so my goal was to find an approximation for the area under the V-curve between times 0 and 4. So to do that, I'm going to add up the areas of these rectangles. So I split up my picture into 4 rectangles, and you can see I'm going to add together the areas of those 4 rectangles, 1 plus 1 1/8 plus 1 1/2 plus 2 1/8, to get an approximation of 5 3/4. We call this the left-hand rectangular approximation method, because I had my rectangles touch at their top left corner. That's where the left comes from. And rectangle, obviously, because I used rectangles to try to fill in that space underneath my curve. I could, instead, have made my rectangles touch at their top right corner, and we call that the right-hand rectangular approximation method. So here's what that looks like. See how these rectangles touch at their top right corners. All right, so we see these rectangles touch at their top right corner. So I get a different answer when I add up the areas of these rectangles. But you can tell it's not that surprising that I got different answers. These rectangles all happen to be a little bit too big. From my left-hand rectangles, those were all a little bit too small. You see this space. Each one of those had a little bit of space between the top of the rectangle and the curve. But they're both just methods of getting an approximation. I could even have done it a different way. I can have my rectangles, instead of touching at either the left-hand corner or the right-hand corner, I can have my rectangles touch halfway along their interval. Let's see. So notice this first rectangle was supposed to cover from time 0 to time 1, but instead of having it touch the curve at the place where x is 0 or 1, I made this rectangle touch the curve at the place where x is halfway between 0 and 1. So halfway between 0 and 1 is 1/2, or 0.5. And you can see that when the input is 1/2, that's the output I've chosen to give the height of my rectangle. You can see the table of values I have here. So here, I will, most of the time, if I use midpoint rectangles, I'll have a little bit extra work to do to figure out those values, just because I'm not happen to be using an integer in my input function. But if I were a computer or a calculator, I don't mind having that extra work to do. I still have this same process. I'm going to make my rectangle touch the top of the curve, the top of my rectangle touch the curve. I'm going to figure out how wide and how tall my rectangle is, do those multiplications, and add up the areas. And this time I got an answer that happens to be in between the LRAM answer I got and the RRAM answer. So here, when I add up those areas, I get 6.625. So I have lots of options about where to have my rectangles touch the curve. And I have options about how accurate how much work I want to do versus how accurate I need my answer to be. If I needed my answer to be more accurate, have you guessed? I'm going to make more rectangles. So there's a nice connection here to first semester calculus. First semester calculus, we were trying to find the slope of a curve, and we could do that if we picked 2 points, but if our points were far away, we weren't getting a very good answer. If we wanted our answer to be more accurate, we would let the 2 points get closer and closer together. We really wanted them to be the same point, so a distance of 0. but we let them get closer and closer. So we have this other, in second semester, we're trying to find areas under curves. We have this idea that's going to connect really nicely. It's really beautiful. If I want a better approximation of the area under a curve, I'm going to use more rectangles. So in all of the examples we did above, we were using 4 rectangles. What if I use 8 rectangles? You can see these happen to be 8 rectangles touching at their midpoints. I'm going to get an answer that's going to be closer and closer and closer to the exact value. This is one of those curves that we'll be able to find the area under it exactly using some calculus that we're going to learn in sections 5.2 and 5.3 and 5.4. But here, this answer is closer. It's kind of surprisingly close, given that we've only done addition and multiplication to figure it out. So just a couple of words to know. These words haven't shown up on the AP test in a long time, like 20 years. I'm going to let you know what they are just in case. Inscribed means all the rectangles are below. All the rectangles are contained within the curve. Circumscribed means all the rectangles are higher than. Every part of the rectangle is, every rectangle is higher than the curve. So that's one way to describe to somebody how they should choose their rectangles. But it's not common, it's not even not common, it doesn't happen on the AP test anymore. So I want you to go back to your notes papers and we're going to talk about how you're going to see this problem on the AP test. So on your notes paper, if you're going to have to use one of these rectangle approximation methods on the AP test, you will. They'll be very clear that it should be an approximation, that you should use rectangles. They'll tell you exactly how many rectangles to use, and they will tell you where to have those rectangles touch. If you don't find that information in the problem, then it's probably not an approximation problem. You're probably supposed to find an exact answer. But you will see one of these abbreviation words, MRAM, LRAM, or RRAM. You'll be told how many rectangles. Or you might see this other word that we're going to talk about in a second, Riemann sum. That's a shorthand way of saying any one of those types of rectangle methods. So let's practice actually drawing those rectangles in, because it's that to find the area of a rectangle and then to add up a bunch of area rectangles is not difficult. What's tricky is making sure you drew your rectangles correctly. So let's practice that a little bit. So you see this problem in the middle of your page here. I have 3 copies of the same picture. It says draw in the correct number of rectangles with the correct heights for each graph for the purpose of estimating the area under the curve from x equals 0 to x equals 6. So first one, let's put me up here. This says draw in 6 rectangles whose top left corners touch the curve. Here's a hint, one of the rectangles will have a height of 0. So, and they won't try to mess with you on the AP test. I'm supposed to use 6 rectangles to cover from 0 to 6, so that's a pretty easy way to split that up. I'm going to have one rectangle cover from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6. That'll be 6 rectangles. And what do I do to make my rectangles touch at the top left corner? I'm going to need to think about, for each of those 6 rectangles, what's the furthest left x in the interval? So if my first rectangle covers from 0 to 1, the smallest number in that interval, the smallest x value, the furthest left x value is 0. So I'm going to make my rectangle as tall as the y value when x is 0. So when x is 0, it looks here like I have 0, 0 on this graph, which means I'm going to make the height of this rectangle 0. So I already found my answer to the hint. It's my first rectangle that has a height of 0. My second rectangle is supposed to cover from 1 to 2. The furthest left side of that interval is 1. So I'm going to use a height of the rectangle that's equal to the y value when x is 1. So when x is 1, it looks like I have y equals 5. I'm going to make my whole rectangle have a, oops, I missed a little bit. My rectangle is going to have a height of, oh my gosh, there we go, a height of 5. My next rectangle covers from 2 to 3. I'm going to go to the place where x equals 2, and I see that's my height. I'm going to draw straight across to make a rectangle. Looks like the height is maybe 16. My next rectangle covers from 3 to 4, so I go to the place where x is 3. I find the height. Looks like maybe 27. I'm going to draw straight across. And then my rectangle is supposed to cover from 3 to 4, and in this case have a height of 27. So far, every rectangle I've drawn is too small. And in the example I did in the slide with LRAM, every rectangle happened to be too small. We'll talk about when that happens, but here, the next rectangle I need to draw covers from 4 to 5, so I'm going to go to the place where x equals 4, go up to the height. The height is more than 30. Looks like 32 or 33. That's going to be my height. Even though this rectangle is too big and all the other ones have been too small, that's not how I make my decision. I have to make my decision on what height to use. I need my left-hand corner to touch. So this rectangle that covers from 4 to 5 has a height of like 32 or 33. The next rectangle covers from 5 to 6. I'm going to go to the place where x equals 5, and it looks like a height of 25, so that's my 6th rectangle. I'm going to let you do the middle picture, and I'm going to come over here and do this last picture. I need 2 rectangles that touch at their midpoint. All right, so I need to go from 0 to 6 using 2 rectangles. So one rectangle is going to go from 0 to 3, and the other rectangle is going to go from 3 to 6. And I want to choose as my height of the rectangle the output value that is halfway along that interval. So my first rectangle covers from 0 to 3. The midpoint of 0 to 3 is 1.5. I'm going to go to the place where x is 1.5. I'm going to draw up here. Looks like, I don't know, maybe that's even 1.5. Is that 10? Yeah, I think that seems like 10. So that's my midpoint. I'm going to use 10 as the height of my rectangle. The rectangle needs to cover from 0 to 3. My next rectangle covers from 3 to 6. Halfway between 3 and 6 is 4.5. I'm going to go to 4.5. I'm going to go all the way up to the top. That looks about right. I'm going to use that as my height and have my rectangle cover from 0 to 3. So if I now wanted to find an approximation of that area, I'd find the area of this rectangle, which looks like 6. I would find the area of this rectangle, which looks like 1, 2, 3 times 29. I'd do that multiplication. I'd add it to 6. That would be my approximation for the area under the curve. Make sure you go back and try that one on your own.